So good morning to all of you. So my third lecture, and this topic is application of Raman spectroscopy. So far you have been hearing how the baseline is prepared, how the background is prepared. Remember, all the application comes after the development of the spectroscopy, and the development of the spectroscopy, such kind of efforts are necessary that Professor Hiramasu has been showing. If those things are not there, you don't see all these things. In reality, you see this one more attractive than the development. But in reality, it is also true, those things are more difficult than this one. So there are two aspects that we always get confused. So this is not the application of Raman spectroscopy in medicinal field, but I felt that this is a good time to convey one message. The message is that most of the time you feel attracted towards the discovery. So if you go to a school for judging an event, then the school teacher will tell that this kid is amazing, this kid has discovered something, that kid has discovered something, and then they try to prove that this is a real discovery. In that way, you actually damage the whole new generation. Instead of telling the kid that you have discovered something, you have to make sure the kid understands the discovery comes out of hard work, out of concrete understanding of the topic. Discovery doesn't come just like that. So this 2 days lecture, whatever you have seen that how this Raman spectroscopy is established. So after all this establishment, now you will see that how the Raman spectroscopy will be used in medicinal field. So to convey that discovery does not come in a day, or they are not achieved overnight, or a achievement of a single person's work. Even though you always see one Nobel Prize, one person got, or the C.V. Raman's, I have shown that another person's contribution was also hidden. So all the time you feel like this person is the main reason for this whole discovery. So I wanted to show with that some popular discoveries that all of you know. You see, nowadays we all use LED. And when I was kid, we brought up in a hurricane, and that tungsten bulb has come. This is the tungsten bulb. Where is the stick? Oh, okay. So these are the tungsten bulb. So after some days we started using that one. When I was in class 7, 8 or like that, we started using this one, and we are so happy that new discovery has come, and we started enjoying that one. And then after some time, government start propagating for these, and then fluorescent light, and then now government wants that everything should be changed by LED. Now, and you know that there was a Nobel Prize on LED. So you feel like somebody all of a sudden discovered. Now you see the series of event for incandescent light for this one. Back in 1745 to 1827, there was a scientist, Volta. You know the name Volta. He did some work on this tungsten light. So it is in that maybe 1800 or something like that. And then this Professor Schwann, after this, he expired 1827, and his birth is 1828. Again he started working on this, and he has done some 1860 at 18 primitive electric light has come, then filament of carbonized paper and some contribution. But we all know, whenever we ask, we all know that who is the discoverer? Edison. But nobody knows that there is another 150 years people have, these are the main popular people. many more people have contributed to come to this stage. So it is not that he all of a sudden one day came and then discovered the tungsten bulb. It's years necessary to come to this one. He has definitely depended on the findings of this at least of these two people. So after that he could come out, because he has some engineering mind also. He knows how to assemble, how to do these things. So he is also a businessman. So he always has a mind that he has to get something so that people can buy. But maybe these people didn't have that mindset. They just enjoyed doing some science. So the fundamental discoveries is a culmination of collective effort. This is very important to understand. It's not a single person's effort. It is a collective effort. And it takes time. It's not just one day it happens. A kid cannot discover because he or she doesn't have that appropriate background. What is done in the reality in the school? One school teacher search a Google and he finds something using potato, get some generator of some volt, and he teach that one to the students, and students show as if he has discovered it. It's just a kind of corruption. The teacher wanted to show that my students are very bright and then they are doing something, but in this way you actually harm the next generation. So since you are adult, so you should understand. So for that I am showing some real incident. Now this compact CFL and the timeline of the invention, see 1840 to 1879, Geissler, he has made something, Geissler tube. So we are talking about the CFL. And then almost after this, there is a Hewitt. He also did some work. So started in say 1830 or 1840, and it keeps on. And then during this time, this American engineer, we actually got the first compact fluorescence light in our daily life. So it is as if it happened in 2000, around 2000. But the history says that these people already have contributed on this fundamentals base he has created in long back. So definitely he has used their knowledge also, and then he got it. He is American engineer, obviously he will be businessman. You know, all Americans are predominantly business. They don't care about other things. Right now also we are seeing that all of a sudden they are throwing Ukraine out and they are becoming Russian part. So anyway, these are, so you can't say like who is the inventor. Inventor means like we feel like I am the one who is doing everything and is come from the very new things. No, my knowledge is also based on somebody's finding. Many times we don't realize that one. And if you do not realize, then you will end up with the things that one day you will invent without having a proper background. So Professor C.V. Raman's base was also created by Ralix, then Smickel. Their work also contributed in C.V. Raman's ultimate discovery. And you see that the LED, 2014, the Nobel Prize went to this two Japanese professors, Akasaki and Amano and Nakamura, I think three people. So they got in 2014, very recent. Now if you see this one, I collected from Google. It started in, at least Google has the information, 1927. One Russian inventor reports the creation of first LED, published the theories of his finding. 1927, so long back he has started, he reported some new finding. After that, 1958, some people created the first green LED. 1962, red LED. 1971, somewhat blue LED. 1972, first yellow LED. 1986, working blue LED. So these are all laboratory one. So he started working blue LED. 1993, this same professor who got this one, Nobel Prize. High quality gallium nitride based blue LED. And then in 2008, LED lights start becoming popular for common use. And 2014, they got the Nobel Prize. And 2019, LED is the main source. 2019, LED is the main source. So you see, such a long history. What I expect is that one day all of a sudden I will just discover LED. And government pump money, you discover. And then we think that we dream that we discover. Discovery doesn't come in a day. Many people are involved. Many knowledges are involved. You have to prepare yourself first. You have to gather the knowledge. And when you have maturity, then you can think of bringing something new. Just because you want to discover, discovery doesn't come. So today's topic is something about the application of Raman spectroscopy. So it's just application. An application of Raman spectroscopy, and Raman spectroscopy you have heard that it's not that easy. It needs so much understanding. Just because you are seeing a peak, you cannot do something innovative because you have to understand the peak. Or somebody should help you to understand the peak. It is not possible for you to do the application as well as to make the fundamentals basis of the Raman spectroscopy. So today this topic is just application. So in medicinal chemistry you have two parts. One is the clinical diagnosis, another is the treatment. So Raman spectroscopy useful in these regards. The most interesting part of Raman spectroscopy is that you do not need to prepare the sample. That is very unique. In other cases, you have to take out the blood, you have to separate the serum, you have to do something, some preparation is necessary. In Raman, in none of the cases, usually you will see that it doesn't need any preparation. You directly measure it. So it is level free, means you don't have to use something else like fluorescence based technique. You have to use a fluorescence tagging so that the molecule which is non-fluorescent, you tag it with a fluorescent moiety and then you start observing the fluorescence. But Raman, you have seen the Raman depends on the vibration. Vibration, every molecule will have some vibration. You pick up a particular vibration which is easy to monitor or which you are interested in. So Raman doesn't need any extra tagging by another molecule. So it is a level free. It is non-invasive. You just can shine that laser light. Laser light, you should not have a feeling that it burns. Laser light like this laser light, these are all not harmful for your body. This is a mild dose in millijoule, microjoule. And often it doesn't require sample preparation or sometimes some simple sample preparation. It is not a gamma radiation or something that no exposure radiation. Real-time monitoring capability, you shine it, get the Raman scattering, analyze it. And characteristic Raman spectra for biomolecules having a distinct chemical identity and unique molecular structure. So Raman depends on the molecular structure. And the molecule which is responsible for your disease or some effect, that molecule you can directly characterize by Raman spectroscopy. So since it gives you the molecular fingerprinting, so it provides precise molecular identification and can provide both quantitative and qualitative. He has just shown you how to measure that one in quantitative manner. So some examples are, this is identifying the polymorphs. Polymorphs, as he has already discussed, is the existence of a molecule in different structure. The molecule is the same. Molecule is same, say stilbene. Stilbene is a molecule. It can stay in a cis conformation. It can stay in a trans conformation or gauche. So the same molecule in different conformation. That's called polymorph. Polymorph is important. Is important particularly in medicinal chemistry, means in drug, that is even very important, because it is seen that molecule is same, but this effect on your body depends on the what is the conformation. So same molecule, one conformation doesn't work for the purpose you are taking, but another conformation works. So in pharmaceutics, it is very important for them to make sure the conformation is correct. So this is one example. In this example, this carbamazepine, that is a medicine. This is a medicine used for some bipolar disease. It has two forms, form 2 and form 1. So in this, it is seen that form 3, it shows the desirable effect. So it is necessary to understand that in the tablet, how much form 1 is there and how much form 3 is there. So if you take an image of the tablet, Raman image means you are monitoring that molecule in the tablet. So you have two forms, form 3 and form 1, and I just said form 3, this red one shows the effect for the disease. So we want form 3. So form 3 is red, so this is the form 3 spectrum, and this blue one is that form 1. So, and this is the image, of the tablet. Okay. So now how this image is generated? This image is generated out of observing a particular vibration of that molecule you are interested. Since the conformation is different, so you will have at least a few vibrations, whether it is a torsional vibration or some other vibration. So you will have a few vibration which differs from one to another, and monitor the vibration. Using the vibration, you make an image of that tablet, and then you can tell that where is what. So form 2, it is seen that form 1 is predominant in that, and form 3 is these things. Okay, these are the form 3. So this allows you to tell that how effective will be the tablet, because if the form 1 is most of the cases, then it is expected that it is not that effective. That is why you will be seeing that drug made in India, but it is supposed to be exported to developed country, their effect is quite different than drug made in India and available for our country. The price is also very different, because you need to consider these things. In this tablet, your effective part is only this much, and that is why you pay small amount of money, and when you want to export it, then maybe your effective things should increase, and that means purification and all these things increase, so you have to pay more money. So regarding the polymorphism, I will discuss this one in the last lecture, that I have some work in the polymorphism using the Raman spectroscopy. This is nothing to do with the medicine. This is just my work, and this I will be discussing in the last one. This molecule is known as ionic liquid. So this is the imidazolium cation, and this one is the anion. In this case, anion is simply monoatomic chloride and bromide. So it is seen that this molecule with chlorine or bromide, so when you do the crystallization, it's long back initial stage word. So when we do the crystallization, then it is seen that this molecule bromine chloride crystallized in two forms. This is ionic liquid, but you can crystallize it at low temperature. So this we said crystal 1, and this is a crystal 2. So initially we didn't have any idea, except that visually it looks different. So these two difference, and then The beauty of Raman spectroscopy is that you don't have to do anything. You just take the sample, put it under laser and get the spectrum. So when you do this one, then we see the crystal 1, this record spectrum is like this, green one, and crystal 2 spectrum is like this. You see there is a lot of difference. Molecule is the same. Molecule is the same, but they crystallized in different form, and when you take the Raman spectrum of this one, we get the green one, and when you take the Raman spectrum of this one, we get the red one, and if you overlap these two, and you see there is a quite distinct difference. So the band which shows the difference and which can be identified for the reason, ultimately you have to find, it's not always necessary, as he said, in case of glucose, without identification of the band, you can still go ahead for the quantification. But in this case, you have to identify what is the reason for the band. If you can identify, and then if you see that these bands are quite different, like 625 band, this is not predominantly here, but 6-3 band is there in the crystal 2, it is absent here. Similarly, 730 band and 701 band. So they are different. So this Raman spectroscopy says that by studying the Raman spectroscopy, you can study these two molecules separately. Now it so happened that in crystal 1, we have got a X-ray structure, so we came to know what is the exact conformation of this one. That was a trans-trans. This was trans and this was trans conformation, and this one we could not get a XRD structure. So this one we found that it resembled to the bimine bromide structure. Bimine bromide structure, it's resembled because it resembled this and this resembled. See, this marker band is here, this marker band is here. So by just Raman spectroscopic study, we say that this conformation is same as the bimine chloride crystal 2 conformation. So this is the way one can find the lots of information about the polymorphs. Without, you cannot do in you cannot use this one in other spectroscopic technique like NMR, because NMR you have to dissolve it. So this is Raman is very beautiful for this purpose, polymorphism. Monitoring the distribution of compound during the formulation is the same again. So this is one tablet having 8 vitamins. 8 vitamins, and these are the components. These are the components. So this tablet has these components: vitamin B12, orange arome, chromium, chloride, citric acid, vitamin B3, and all these things. So now in tablet you can find out which vitamins is distributed in which way, like just color coding. Say this one is this one, and say vitamin B3 is this one. So you can see the distribution of different component in the tablet. And this one, it is not, remember, it is not an image. It is not that you take a camera, you keep the tablet, take a camera and then take a photo and you get this photo. This is the molecule's presence. You are seeing the presence of the molecule observed by their vibration of bond or vibration of that angle. So it's a fingerprint. So this presence of this red means this component. Presence of this means this component is distributed like this. So this is one of the most authentic way, because you are looking at the molecule. You can study the surface of a tablet. This is the surface of a tablet when you take an image by normal camera. This one, I think this is the tablets, this it's at center for breaking that part. Maybe that is the one here. Anyway, this is the tablet, and see this tablet you will have various active pharmaceutical ingredient. So if this tablet has say 3 component, 3 API, what are these? Aspirin, paracetamol and caffeine. These 3 APIs are there that constitute the whole tablet. And you can have the independent Raman spectra for this component. So this color is aspirin, this is the aspirin, then this is the paracetamol, aspirin, and this is the caffeine. Okay. Now you want to make an image of this surface to see the distribution of these components. Now for that you pick up a vibrational signature band, just like marker band I have told in the C strands. So you have to pick up a signature band. So signature band for aspirin, they have taken the CC breathing band, and then they have observed where are the CC breathing bands are seen on the surface by Raman spectroscopy, and they are saying this color, these are the color, they are saying this way is distributed, and then this one is paracetamol, predominantly paracetamol on the surface, and then this one is caffeine. So green one, this is the one. So this is this one, this color is this one, and paracetamol is this one. So we know how the components are distributed. So this is called tracking the active ingredients. So in manufacturing the tablet, often you have to make sure that tablet do not have any defect. Tablet doesn't contain some other things which may arise due to the production. In production unit, if you have some other component inside, that will come definitely on the tablet, since tablet is taken. So you have to make sure that tablet doesn't have any other component than whatever is required. In this case, that Raman spectroscopy can characterize the defect or presence of some other things. So what happened, you see this is not that clear here. There is some visible some pattern difference, and it doesn't compliance with that expected result. So if you do the Raman spectroscopic studies, then it is seen that there is some presence of charcoal. This is the spectrum you have taken for this part. This one is the spectrum you have taken. So this is the spectrum of this part of the tablet, and you see it is not as expected from this API spectrum. API spectrum means that active ingredient that you are expecting, that spectrum is this one, but your tablet spectrum is this one. Then you have to think why this spectrum, that final product spectrum, is quite different than the expected API. It is seen for this particular case that somehow charcoal has come into the tablet. You have to check with all the things you are using. Charcoal is used mainly for the purification of the organic compound. So maybe they have used in some part charcoal, and that charcoal has come into this final tablet format, and they have identified. They have taken the charcoal separately, and then they seeing that this and this has a charcoal influence. So charcoal is present. Then you have to again revise your whole process so that this becomes charcoal free. So this is a nice example. One can do this nasal spray analysis. Nasal spray was very popular during this corona. So in that also you can analyze the nasal sprays, these droplets. These droplets can be analyzed. So these are the two components you are expecting, and whether these two components are there in the spray. So that is shown in this paper. So nasal spray analysis by the Raman spectroscopy. And often you know that this drug, if you keep it open, then it goes bad. So some drug which needs to be protected from the humidity exposure, so that you can have a study. Raman is a good way of studying whether the drug, whether the molecule has absorbed water or not. For example, this Raman spectra of anhydrous lactose and lactose with monohydrated lactose, they are quite different. This blue one is the anhydrous and this is monohydrated. You see their spectrum is quite different. Even the molecule is same, but because of this water molecule, there is change in the structure, and that influences the final outcome of the Raman spectrum. And that allows you to tell that this lactose, which is supposed to be anhydrous for some particular purpose, has some water molecule. So if water molecule is not allowed for the purpose, then you have to change the whole process. So this one is sometime biotherapeutics means that these ingredients are taken from the live cell. So their stability also can be studied. So Raman analysis of lysozyme and in pH 4, and this, if there is a 20% ethanol water, then it is seen that it changes the structure. So things are changed. So that means that this was said that distinct Raman signature bands were identified. So this drug at pH is different than this drug at pH 4 with 20% ethanol. That means drug molecule structure has changed. So this is a new information for the that we can obtain only from Raman spectroscopy. So this is there will be few examples in which this Raman will allow you to see whether the drug is stable or not. Drug often, with the time or with the exposure to the sunlight, with the exposure of the humidity or air, oxygen, whether drug is stable or not, that Raman can easily say. So the first example is that this acetaminophen and paraminophenol. So you have this is a drug, and this drug is used for the pain reliever. So this one is the acetaminophen, and this one, I zoom it. No, zoom option is not there, seems. Okay, so this part, if you look at this part, so this is your drug, and this drug is found to be decomposed with this one. So this is the paraminophenol. This is aminophenol. So this drug decomposes to this component. So this can be detected by the Raman. So it means drug is not stable. So you can see some peaks, and then you see that these peaks are changed. So this degradation means your drug is not stable. So that means even if you take, it won't affect, or it won't affect in the way you are expecting, because the drug, amount of drug is decreasing. And if this component is bad for your health, that means taking drug is even bad for your health. This is another example that this is azithromycin and it changes to azithromycin A. So this is also very complicated, but the thing is that this drug also decomposes, and the decomposition process can be identified by taking the Raman spectrum. These are another two examples of the same process, that they are not stable. This is your drug, and it is seen that it decomposes to this, and that process, that what is the initial drug, and then final one, this process can be identified in the Raman's experiment. And in this case, they have used 500 milliwatt excitation source, and the excitation source is 1064 nanometer, which is usually we don't use, but this has a good thing is that this gives less fluorescent, so many people prefer 1064. But as Professor Hiramasu said, that the more wavelength you use, intensity decreases. But to remove the fluorescence, many people go for the longer excitation. And the resolution is 8 wave number resolution, 5 minutes acquisition. So this kind of condition once only I have given to make sure that you understand that what kind of conditions are used. So 500 milliwatt, it is not a very strong power, but it is strong for the biological cell. This is okay, this is a molecules, so chemicals, so that's okay. But for biological cell, even we have to use millijoule, a microwatt. So this is the excited source is not that popular. Usually we use 532 nanometer, 633 nanometer or 785. But they have used 1064. And this one is the resolution, how this one width is 8 wave number. 8 wave number is quite good. You can have in specific case even 1 wave number also, but in general 8 wave number is quite good. And 5 minutes is acquisition time, means total 5 minutes you have used for getting this spectrum. Key peaks you have to find out. In normal cases, what you have to do, you have to find out the key peaks which changes, and then you have to do the assignment also. What are the reason for that peak? That assignment nowadays we do using the calculation. There is some package is available, Gaussian package. You have to just draw the molecules and do the optimization, and the computer will give you these frequencies. Computer will give you the calculated spectrum, and then computer also will give you the where the spectrum bands are coming. So you can just check you overlap with your spectrum and check the position, and then you know computer will give you that what kind of vibration is responsible for this band. They will give a movie that molecule is how molecule is vibrating. So with that you have to match up, and then you have to tell that which vibration is responsible for which peaks. So this is necessary, this is a common practice people do. Once only you have to do, after that you know that which is for what. So this is another example that this kind of changes. So this molecule, this is a drug molecule, it changes to non-drug molecule. So these things, so these are the things. So what is the degradation change? SARS, maybe he will be speaking on the SARS. SARS is a new Raman technique. SARS means surface enhanced Raman spectroscopy. So Raman signal get enhanced due to the presence of some particular surface. So it is seen that it enhances several fold. So that's why SARS is a very now important technique. But remember, for SARS you have to do some sample preparation. So for Raman you do not need to, usually you do not need to do sample preparation, but for SARS, because you have to make sure that this molecule is in touch with the surface, appropriate surface. So SARS, since this SARS gives enhancement of the radiation, several fold enhancement of the radiation, in many cases people do the experiment with the SARS to identify something. So this one is one example that this anti-cancer drug studies in human blood. So good thing with that is that even in presence of the this blood is a complex substance. In presence of that, one can study a particular molecule, like this molecule. This molecule you can study in presence of blood. It's not that you are studying this molecule separated. You are putting this molecule in a hexane or acetonitrile and study. That is different than in actual field studying. So this they have shown that SARS helps. These are all this kind of data. So many, whenever this purpose of showing this one is not that you have to understand everything, but when somebody says that I have detected something in somewhere, so that means he has done many these things. And whatever Professor Hiramasu said, so many spectrum you have to record, you have to understand that spectrum, you have to analyze the spectrum. Particularly in case of medicinal chemistry analysis, you have to make sure that you have do some kind of good analysis using some program, because this is for human health. You cannot just like that tell this is suitable for the consumption or like that. So lots of mathematics are also involved in that. So tobacco related biomarker in urine also can be found out with the help of this one as well as TLC. TLC means thin layer chromatography. This one says that you have seen the big Raman microscope, and you see this is handheld. And this handheld is enough to identify the drug in urine. So if somebody consume drug specifically in the sports, so this is one technique. You see this device is so small, but this device is able to detect. Why? Because this device is meant for particular one detection. It is not meant for the whole Raman spectrum and any kind of sample and the high resolution. No, this is meant for some particular purpose. So you have a Raman spectrometer like this also. So this is the drug in human urine can be detected. This is the same portable kit, and some synthesized drug like these are the drugs. Synthesized drugs also can be detected based on this Raman spectrum. This one is a bit interesting. So what this says is that you want to detect the hydrogen. Hydrogen is explosive, so hydrogen is not good in many systems. So this one they are detecting based on the SARS. What they do, this hydrogen they react with another one chemicals, phthalimide aldehyde, and then this molecule forms. So this one is the one that we detect. This one is the one that we want to detect through SARS, surface enhanced Raman spectroscopy. We are not using this one on the surface directly. What they had done is that they have made a complex with this another organic molecule, and it is found that this organic molecule, this complex, makes a strong binding with this surface, and then we get an enhanced Raman signal. So you see, you are getting an enhanced Raman signal. Enhanced Raman signal means the more is the enhanced Raman signal, smaller amount of compound you can identify. So this is a nice way of detecting hydrogens. So this is the one. So this key advantage you see, high selectivity, low cost, and fast analysis time. Is very strong, so it's fast analysis, and cost is low because this organic molecule is cheap. This cost is low. So what happens is that if you have a mixture of compound in that, this hydrogen will react with this one. And then you make a polish of this mixture on the silver nanoparticle, that is your surface of the SARS, and then you get the enhanced Raman spectrum. So this, in addition to hydrogen, you can use, these are the other molecules that you can find out. So you see this, these are the molecules without SARS measurement, and this is with SARS measurement, and this gives a quite strong signal. This hydrogen can be found in presence of other element. That is very important, because in reality this explosive or drug will be in addition to other molecules, so it should be detected in presence of other molecule which otherwise interfere. So hydrogen is found detected in real field, that is lake water. This lake water in presence of hydrogen, this is clearly showing the band. So it is very popular field that people want to know whether the cancerous cell is present in human body or not by Raman spectroscopy. Usually for the cancerous cell determination, you have to do biopsy. Biopsy means you have to cut that part and then send it for the laboratory. But this Raman can give easily that different cell. Cancerous cell means there is some component in the cell which is different than the normal cell. Okay. So that component, if you can identify by the Raman spectrum, that's nice. So for that you don't have to do any cut, you just have to shine that laser. Laser can be shined or focused on anywhere in your body, even in the deep, in the lungs. You have to just focus on the lungs, and then from there, this whatever scattered radiation comes, that you have to collect from on the top of the body. On your body, the objectives will be there, so they will focus and they will collect. So what you have to do is that you have to analyze the spectrum. First you have to know what is the normal spectrum, and then you have to analyze, you have to find out the abnormal spectrum because of the abnormal composition of the cell. So this one is that gastric cancer cell. So this is the image, and these are the, you see, in reality you have such a noisy spectrum. So there are A, B and C. C is the difference between A and B. One is that normal cell, another is the cancerous cell. So in this field you have to do many more recordings. You should have a strong database. It is not that everybody's cell pattern is same. So you should have a huge database, and then you have to find out what is the Raman spectrum for that kind of cell that you are here. It is a gastric. So in this, what is in this kind of cell, what is the normal cell? Normal cell Raman spectrum, and then you have to find, when some patient has come, you take a Raman spectrum of that cell. You do not need to cut anything, just shine the laser, excite that part and get the scattering, and then you see what is the difference. If the difference is there and the difference indicates towards the cancer, then you can tell, yes, this possibility is there, that there is a significant change of the molecule composition of that cell. So with the data set you can tell that this cell is probably cancerous, carcinogenic. So this is one more. This is a pancreatic cancer cell. So here this normal is gray, this one is the normal cell, Raman spectrum of normal cell, and the black one is the malignant cancerous cell. You see there is a significant difference. If you keep on seeing these things, whenever Raman spectrum you see, you have to see all the bands and to find out where are the differences. So you see the difference, here is the difference. This black one is the malignant. So you see that in normal cell there is a peak here, but there is no peak in the black one. Here also it is different. They are different. Everywhere you see, if you keep on looking at, you will see. Now, another way of seeing is that there is a peak in both the cases. Then you have to see relative intensity. So, this is one. And peak position is there, in both the peaks position is there, but relative intensity if you calculate, then it is quite different, isn't it? So it's not just peak position, shift of peak, it is also relative intensity is important. So you see that here peak intensity has increased, but it is decreased, and in this, except maybe this one, almost everywhere there is a significant change. So if there is a significant change and if your database is established means that database says that this is the common Raman spectrum of a healthy cell, and this one is that common Raman spectrum of a malignant cell, then you can tell, if unknown patient has this kind of spectrum, then you can tell yes, there is a possibility that yours is cancerous cells is detected. This one I have shown to show that how nicely these people are seeing the peak. Even the shape they are determining. Change of peak position, small peak position also they are determining. This change in is determining. So whenever you want to compare, you have to compare thoroughly, not overlook. You have to see everything, every peaks you have to see, and then where are the changes. And then you have to find out the peaks which is a marker peak. For that, lots of studies has to be done. These are the final result of the studies. This again cancerous one, and this is also Parkinson disease, that they demand that early detection is possible using the Raman spectroscopy. These all references are there. So this is taken from some references. So every slide has a reference. So this is Alzheimer disease. That one is a Parkinson. This is the Alzheimer. And the UV Raman is a Raman spectroscopy. When in our instrument we have 532, 633, 785 excitation source. These excitation source all are in visible region. When you have excitation source in UV region like 248, 266, 340, like this excitation source, that if you have that excitation source in the Raman spectrometer, then that is called UV Raman. The beauty of UV Raman is that since you know that intensity increases with the decrease of wavelength, so your scattered intensity is very strong. So peaks are very strong. But bad thing with the UV radiation is that you cannot shine UV in a normal living body. And also they are very powerful, so they usually damage. But whatever necessary for whatever purpose, then you have to choose. UV Raman is very expensive. So this is a few examples, a few applications of UV Raman. So this is some advantages of UV Raman. And this is some detection of some molecule using the UV Raman. And this is again, that's all. Okay. Okay, I'm time. Anything you can ask? We have still 5 minutes. Once more, repeat.
Yes. Sir, how to detect our desired molecule through Raman? Is fluorescent dye enough? Is fluorescent dye also used or enough to vibration and transmission?
In general, Raman when you are using Raman, that means you are focused to the scattering process. And when you are thinking of fluorescence, that means you are thinking of electronic transitions. So, as he said, the fluorescence is a negative process for the Raman. If you have a fluorescence from the sample, when you are exciting the sample for the Raman, that fluorescence will hinder your Raman intensity. So fluorescence has to be eliminated. So for the elimination of fluorescence, one way is that if your 532 nanometer excitation gives you fluorescence, because there is a absorption of that molecule at around 532, then electronic transition will take place, and if there is electronic transition, so you will get a fluorescence. It's a normal process, you cannot avoid. So what is important to do that time is that you choose a wavelength where there is no absorption of that molecule. Say that wavelength is 785. So now you use 785 to excite from here, your maybe this electronic state is here and you are exciting at this wavelength or just opposite. So your electronic state is here, say this is the S1 and this is the S0. So you excite up to this and then this comes back and then you get the Raman spectrum. So in this case fluorescence will be avoided. So you should not have fluorescence. You should try to avoid the fluorescence. If you have a fluorescence, then you have to do this all background correction, that what he has taught you, the baseline correction, that is called baseline correction. Baseline correction is important and it should be scientific way. So there is the baseline is not this. If you have a Raman like this, there is a strong baseline. So instead Raman should be like this on the baseline, no? So you have a baseline, that baseline you have to correct using some polynomial. So mathematics is involved. You correct this baseline with some logic also you have to put, that is a fluorescence or like that, and then baseline has to be corrected to eliminate the fluorescence. So fluorescence is not good for Raman spectrum.
Okay, sir. Sir, one another question. What is the drawback of IR due to which we prefer the Raman, not IR or NMR?
IR?
Sir, my question is that what is the drawback of IR due to which we prefer to Raman, not IR in biological molecule?
Okay, I think he has shown you some slides. IR, applying IR spectroscopy in biology is difficult because IR spectrum is very much susceptible to OH vibration. OH comes from the water. Any biological sample will have water.
Yes,
and in that, this you can think of a window of your study. So if it is say 4000 and if it is say 400, and then you see OH stretching is occupying a huge amount of blocking. So here you cannot observe any signal from biological cell component because it is already OH is occupying, and then you have a 1500, they are also bending motion, that part is also occupying. So you hardly have a free space to study biological sample using the IR.
Okay,
so that's why IR is not good for the biological sample.
thank you, sir.
Also, how can we analyze the quantitative analysis by this?
Okay, so for quantitative analysis you always need a reference compound. Yes.
Okay, so what will be the criteria? How can we identify how much is present in our drug?
So for that, and the same condition, if you want to analyze a molecule, so at the same condition you take the A molecule spectrum and then you take your drug spectrum and then you can compare the intensity ratio. But the condition should be same.
Okay, but intensity can be changed with the variations of solvent. So if we take a same area in a different we change the intensity?
Usually in drug you do not use solvent. It is a solid, usually. Yeah,
If you use a pelleter form, like a liquid form, so how can we?
liquid form means drug in pure liquid or drug in solvent.
Drug in pure liquid.
Okay, in that case this A molecule also you have to take in the same condition. This A molecule in the pure liquid. Some known concentration, say 5%. So 5% A molecule in the pure liquid gives you this kind of band. And then what is your unknown that solution, whether it is giving more or less. Compare, direct compare. If you take exactly same condition, you can make a direct comparison. Exactly same condition means condition of the sample preparation, condition of the instrumentation. Your excitation wavelength, your slit width, your acquisition time, number of acquisition, everything should be same. Raman as such is intensity is very difficult issue because Raman that cross section is depends on the molecule. Raman cross section. So intensity part is complicated, but you can have a comparative one.